name is Qinshan Chu. I am a PhD candidate from the Ohio State University. Today I'm going to present this paper, the NV group link efficient reductions for distributed deep learning on modern dense GPU systems. So today I'll be covering a few things. First, I'll talk about the trend we have seen in the past few years about the modern HPC systems. Then I'll talk about the Allreduce, which is very important operations for distributed deep learning. And we talk about what's the limitation of current Allreduce for dense GPU systems. And it leads to the research challenge we're trying to address in this paper. With that, then we talk about the proposed designs. We call it NV group Allreduce. Then I'll share some performance numbers and conclude the talk. So in many years, HPC architectures keep evolving. From many years back, we've been using multi-core, many-core processors like Intel Xeon processor or IBM Power 9 processor. Then all connected these machines using high-performance interconnects like InfiniBand, OmniPath. In recent years, we've been widely deploying the accelerators, such as GPUs. Maybe in the next few years will be something like FPGA or some other accelerators. And of course, you have the storage devices. And one thing I want to highlight in this slide is the supercomputers you've been seeing recently. They're all powered by the GPUs. For example, the #1 Summit system is actually powered by more than 27,000 GPUs. Same thing for like #2 Sierra, Lassen, is ABCI. They're all powered by thousands of GPUs. So once you have these large scale and dense GPU systems, there are two things you need to look at. First, like how we scale up. So to scale up, which we usually use the technology called PCIe and NVLink, NVSwitch, these interconnects. For example, the NVIDIA DGX machine, it has 16 GPUs put together in one single machine, one single node. They're all connected by the NVIDIA NVLink and NVSwitch technology. And in the next generation supercomputers, we'll be seeing like AMD GPU using Infinity Fabric and Intel XE-Link. On the other side, when you have so many powerful machines you want to connect together, you need to see how to scale out. So right now we've been using InfiniBand, OmniPath, Ethernet. For example, the IBM power system used on the #1 Summit, it has 6 GPUs per node, and it used InfiniBand to connect more than 4,000 such nodes. So in the next year or so, we probably will be seeing the Cray slingshot for the next generation supercomputer. We'll see how it goes. So with all the powerful HPC systems, these supercomputers, we've been using that for application like distributed deep learning. And now we've been using GPU-enabled distributed deep learning. It is very popular recently thanks to the easy-to-use and high-performance frameworks such as TensorFlow, PyTorch, NXNet, and Haribo, and there are more. It has been powering a wide range of applications, from image classification, speech recognition, self-driving car, healthcare, and climate analytics. A lot, you name it. So here I just put one example. This is from the AC 2018, the Golden Barrel Prize. They're actually using more than 27,000 GPU to perform the climate analytic using a deep learning technique, and it can achieve almost 1 exaflop performance. So if you look at a little bit closer to the distributed deep learning, you know that you probably will see reduction operation being used a lot, especially if you're using data parallelism approach. So here, one example showing here is that if you're using multiple GPUs, is agent here. So each GPU is working on an independent work, different data. Then at some point, you need to synchronize to exchange some gradients and weights. And here we've been using Allreduce. So Allreduce is heavily used here. So you can definitely check out this paper I'm citing here, or other a lot of paper discussing how and why we are using Allreduce. In this paper, we're trying to see that we know Allreduce is important and how we can enhance that. What's the limitation of the current Allreduce algorithms? So we know that current state-of-the-art ring-based Allreduce, that's the most popular algorithm. Then it works like this. You form a ring between the GPUs. GPU send its gradient to the next GPU. That GPU do a reduction locally and send the reduced gradients to the next GPU and so on. So it forms a ring. So the good thing about ring is that it's contention free. Doesn't matter what's your underlying topology. But the problem is always it's not going to scale very well. So please check out our paper for more in-depth analysis for the ring algorithm and other Allreduce algorithm used in the HPC system. Here we focus on the ring, and we see that it cannot really efficiently utilize NVLink. Let me give you an example here. This is like a Summit system. It has 6 GPUs per node, and we connect these. We create a ring to perform the Allreduce, like the red arrows you see here. We create a ring. But earlier we see that, okay, it looks like there's some link, for example, from CPU to this GPU 2 is not going to be used. And also same thing from GPU 1 to GPU 3. This link seems to be idle while performing the ring Allreduce. To confirm this, we use a profiling tool presented in this HiPC paper. And we provide the Allreduce operation using the Spectrum MPI, OpenMPI, MIP2 GDR, and Nico. These are like the state-of-the-art communication libraries used for deep learning and HPC applications. So you can see it's all over the place, and at some place, as we expected, like GPU 1 to GPU 3, there's no traffic here. So then you look at the Nico. It is a pure ring-based algorithm, and as expected, it's not using some NVLink here, like GPU 2 to CPU, GPU 1 to 3. So we learned that all these communication library, they are not able to utilize all the NVLink. But NVLink is very important in these dense GPU systems. So it leads to our research challenge here. We're asking that how can we design a link-efficient Allreduce algorithm that can maximize the utilization of all available hardware communication channels such as NVLink or InfiniBand. And if we can do that, can it boost the performance for distributed deep learning on emerging dense GPU systems? So to answer that, let's look at the proposed design. We call it NV group Allreduce. In NV group Allreduce, we have 3 steps. So first, because we want to utilize all the NVLink, we'll first form the NV group. So NV group, the idea is like we treat multiple GPU as one big powerful GPU. And within a group, we develop a kernel trying to utilize all the NVLink. So this is a cooperative reduction kernel we propose. It is a persistent GPU kernel. It exploits low store primitives over the NVLinks directly. It's a high occupancy kernel. We'll talk about that in a minute. Then once you can utilize all the NVLink within this group, then next one is like how you do the communication across the NV group. So here we employing the ring-based contention-free algorithm over this slower IB network. So let's go it one by one. First, to form NV group is pretty straightforward. We perform the topology detection and GPU grouping. To discover which GPUs are fully connected by NVLink, you can use tools like HardwareLog and NVIDIA Management Library. Here's a link you can check out. It provides API to tell you like is this link between CPU and GPU 1 an NVLink or not. So using these tools, we can figure out the topology. Then we can group them, create a logical GPU groups using a semantic like NPI group or communicator or anything you like. Once you have these groups, then you'll see that if you're using a ring algorithm, for example, you can reduce the dominant performance factor from number of GPUs to number of GPU groups. It's very significant. So once you have this group, the next step is like how we can do the reduction efficiently within a group. So the cooperative reduction kernel, there are two parts. First, CPU going to help a little bit here. So CPU creates work queue for each cooperative thread array. We call it CTA, or some people call it thread block. So it's basically a block of threads. So the basic idea is like, okay, the data, if there are some data chunks need to be reduced, and GPU will assign the work to each CTA, and this CTA will start working on that independently, so there's no dependency there. So like this kernel, basically each CTA will just pull the individual work queue, and each CTA will start doing the reduce if there are requests coming. So if there, for example, if there are two chunks, 0 and 1 coming from other nodes, we store it on the system memory, and now we're trying to do a reduction. Then the first step will be we'll assign some work to CTA 0. You maybe work on the sub chunk of chunk 0, and first step doing the reduction, load the data from CPU over NVLink directly and do a reduction here. Similarly for CTA 1s, and similarly for the GPU 1. Then the next step, we keep doing that because you still need the data from another GPU, so you can load the data directly from GPU 1, do a reduction locally, and store the data on the GPU 0. So it's totally load store directly over NVLink. Is high performance. Then once you are done, this CTA will signal the CPU using this work queue again. This is an implicit synchronization because we are using persistent GPU kernel, so we are not synchronized at the kernel boundary. So we just tell the CPU we are done, then go back to see if there are more work to do. So there are many multiple ways to implement such persistent kernel. Definitely check out this paper. We talk about more detail about how to implement such persistent kernel. And one thing I will highlight is this kernel is high occupancy, like I mentioned earlier, because you can use very low, you can achieve very low register pressure. If you are familiar with CUDA programming, you will know that if you can achieve low register pressure, you can keep high occupancy. Is very important for high performance CUDA kernel. The reason we can do that because CPU coordinates the topology and communication path, all those informations. So GPU doesn't care, doesn't need to know those. So GPU doesn't need to keep those information inside the kernel. So we don't use those registers. So that's why we can enable all the threads in one SN, the streaming multiprocessors, to perform the reduction. To give you an idea, the NV group we propose here, the figure showing here, you can see NV group can use 1K thread in each CTA. 1K thread is basically the maximum number of threads you can use in one SN. And compared to Nico, which can only use around 256 threads per SN, per CTA. So here, each CTA, if I just use one CTA, the proposed NV group can achieve much higher, almost 2 times higher throughput compared to Nico. Similarly, if you're using 2 CTAs, of course, if you go up, at some point you saturate the NVLink, so there's no difference between Nico and NV group. But the reality is that you don't need to use that many CTAs. Then you don't need that high throughput because your bottleneck is not the Allreduce, actually the InfiniBand, the communication over InfiniBand, which is like around 25 gigabytes per second. So 2 CTAs is sufficient for us. So that's why we can have very low SN consumption. So when you launch a kernel, it takes that less time. So you have, because this lower scheduling overhead. Then you can free the resource for the application. Then application, some SN can do the computation, then some SN doing the Allreduce. Finally, we need to do a group-wise communication. It's inter-group communication. Will be using ring-based reduce scatter plus all gather. Will be over the IB or like XBus, like depends on where how's the interconnect between the groups. So the example here is like this, right? This is a reduce scatter algorithm, and once you have some data received from other group, then you will offload the reduction to an NV group, like we just mentioned earlier. Will be the subchunk will be assigned to each GPU, and now this GPU will just do a direct reduce scatter, or it could be a all-gather operation and directly over NVLink. So note that there's no need to use any advanced algorithm because you have everything fully connected. You can just use the direct algorithm without experience any contention. So we have some more optimization techniques. Please check out the paper for more details. Then let me share some performance numbers. We conducted the experiments on 3 systems. First is the number 1 Summit system. It has 6 GPUs per node. And of course, it has NVLink between CPU, between CPU and GPU. Similarly, Vesson, it has 4 GPUs per node. So it's a 3-lane NVLink, and both systems using dual rate Mellanox IBEDR is the IBM Power 9 machine. And another slightly different machine is NVIDIA DGX-2. So it has 16 GPUs per node, all connected by NVLink and vSwitch. It has IBEDR there, but because it's a single node system, so these EDR are not being used. So we compare the proposed design compared to the libraries like Spectrum MPI, OpenMPI plus UCX, MVP2 GDR, and Nico. And for benchmark, we use OSU micro benchmark and the modified Nico test to compare MPI Allreduce to the Nico Allreduce. Application level, we try the Horrible with TensorFlow and PyTorch. And of course, there are some more numbers I skip in the slide. Please check out paper for more performance comparisons. So for the proposed design, the NV group are already made public available under the MVP2 project. So if you check out the MVP2 GDR release, you will see that the design is already there. And this project is powering a lot of top 500 clusters. You can check out the website for more details. So first, we want to see if we are able to utilize all the NVLink. So we did the same experiments again. This time, I add the proposed NV group design. So as you can see the dark bar here, we can achieve much higher throughput in all NVLink, including the one between GPU and CPU. And it's much higher than all the other communication library. So next, the question is, if we can do this, is this going to help the Allreduce? Indeed, it is. We try this on Summit system with Allreduce benchmark using more than 1,500 GPUs. For small message, we have seen around 1.6 lower latency. For large message, we can see up to 1.7 higher bandwidth compared to Nico. Then we also scale much better compared to all the other production libraries. And there we have seen some issue with Spectrum MPI and OpenMPI. We're still trying to resolve that. And at the application level, we tried the Resonate 15 training using Horrible with TensorFlow. This is on DGX-2 machine. We were using the synthetic ImageNet dataset with batch size 16.4 and 100 batches. So we achieved around 9% higher images per second. Then we push the limit a little bit more further compared to Nico, so we can achieve around 93% scaling efficiency. Similarly, on Summit system, we did the same evaluation, and for TensorFlow, we see around 5%. It's not like huge, but it's consistent. But interestingly, if you look at the PyTorch, we have seen around 1.5 higher images per second compared to Nico, and this is with 384 GPUs. To conclude this talk, we know Allreduce is very important. It kind of dominates the performance of distributed deep learning, and we found that ring-based Allreduce is not that efficient. So we propose NVLink Allreduce, which can maximize NVLink utilization, and we are performing the cooperative reduction on GPUs, and it can achieve faster distributed deep learning on dense GPU system for PyTorch and TensorFlow on the Summit system. So all these designs are public available on since LMC2 GDR 232 release. Please definitely check it out. You can download and use it today. With that, I would like to thank you. If you have any questions, please feel free to send us emails, and also check out our project websites for more details. Thank you and goodbye.